Hello, everyone. This is Matt Aslett, Director of Product Marketing at Aerospike. Today, I'd like to welcome you and say thanks for attending today's webcast titled Today's AI ML, Analyzing and Acting Under Real-Time Data. I'd like to introduce today's presenters, including Brent Keator, VP Infrastructure, Nielsen Marketing Cloud. Brent served as the VP of Infrastructure for Exalate for over 2 years before Exalate was acquired by Nielsen in 2015. Prior to that, he worked at Morgan Stanley for the better part of a decade as both a data center infrastructure management consultant and as a Vice President Enterprise Computing Solutions Engineer. Kevin Lyons, Senior VP Digital Technology and Data Science, Nielsen Marketing Cloud, is responsible for managing teams of machine learning engineers, data scientists, analytics, product specialists, and analytics marketing advisors. Prior to Nielsen, he served as VP of Analytics and BI at Rocket Fuel, a big data AI programming media buying platform for digital advertisers. Matt Aslett is Research Director for the Data Platforms and Analytics channel at 451 Research. He has overall responsibility for data platforms and analytics research coverage, which includes operational analytics databases. Matt's a regular speaker at client and industry events and has delivered keynotes and moderated panels, for example, at Strata, Hadoop World, Hadoop Summit, Vercona Live, MySQL Conference, and Graph Connect. Just a few housekeeping items. After the presentation, we'll have a brief Q&A period. To ask questions, simply type it in the question box on your screen below, and we'll get as many in as we can. We'll respond to all unanswered questions via email after the webcast concludes. This presentation and slides will be made available to all attendees once the webinar is complete. And finally, please provide any feedback at the end of the webinar. With that, I'll turn it over to Matt. Matt, take it away.
Thanks, Matt, and thank you everyone for joining us on today's webinar. So yeah, I'm going to kick things off today, just giving us sort of an overview of the state of the market as we see it in terms of AI and machine learning, and a few examples of how we see organizations are obviously putting those to good use in order to act on real-time data. Just briefly before we get into that, I want to give you just an introduction to 451 Research in case anybody's not come across the company before. So we're an IT research and advisory company. We have a couple of hundred employees, including over 120 analysts and over 2,000 clients, which includes technology and service providers, corporate advisory, finance, professional services, and IT decision makers. And the last thing I'll point to here is perhaps the most important in some ways, 85,000 plus. That's the number of IT professionals, business users, and consumers in our 451 Alliance research community. So those are people that are not necessarily direct customers of 451 Research, although many of them work for companies that are, but they are practitioners, people out there in the field, using technology as part of their daily working lives and their home lives, and obviously those are increasingly overlapping. And what they do is they, help shape our view on the world by taking part in surveys and interviews. So an increasingly important part of the organization. If that's something that you'd be interested in return for doing so, they get free access to our research. So do let us know if that's something you'd be interested in getting involved in. So that said, to get into the core presentation itself here, I thought I'd start off by talking about the evolution of analytics and how we've seen sort of obviously some of the technologies, but also some of the sort of attitudes to sort of analytics changing over the last few years. And obviously a lot of that is driven by sort of the idea of big data. And so I wanted to always, you always or very often use this quote from George Dyson, the computer historian, because it kind of puts into context for us what we saw as being different about big data. So a lot of people talk about the volume, variety, velocity of data, and all those things are absolutely relevant. But for us, what it really came down to was actually an economic change, and as described here as being sort of the cost of keeping information becoming less than the cost of throwing it away. Now, obviously we can argue about whether that's true in every case, and this is obviously a generalization, but it is important, I think, in terms of setting the context for the way in which we see organizations taking advantage of data. And here's another sort of chart that kind of illustrates this. And if we think about, for many years, the majority of enterprise data was from transactional applications. We think about that as sort of being a transactional era, and then we moved into what we might think of as the interaction era, where organizations taking advantage of more and more data from web and server logs and mobile applications and social media applications, and now we're very much, I think, within what we might think of as being the engagement era. Things like chatbots, digital assistants, recommendation engines, driving an increasing volume of data, and obviously, we're just on the brink of sort of the next phase of that in terms of sensors and IoT, potentially massively increasing the volume of data there is to be stored. But at the same time, and obviously this is an illustration and again a generalization, but what we see is that the cost of storage over that time frame has also gone down. So whilst there is absolutely more and more data to be stored and processed and analyzed, the cost of doing so, and therefore the opportunities for organizations to store and process all the more data can be realized. The other thing, of course, is it's not really just about how much data you've got. I mean, I think as an industry, perhaps we've fixated a little bit about that on that over the last few years. It's not how much you've got. It's obviously what you do with it and how you take advantage of it that counts. And this is a great illustration of that. Obviously we borrowed from Gaping Void in terms of just illustrating the fact that it's not just the data, it's also how you extract information and apply knowledge and insight and to that, and obviously with a view to generating wisdom and generating business value from that data. And the way in which we see organizations doing that is also sort of changed. If we think about reporting and analytics historically, has actually been very much sort of IT driven. So the IT department or people within that group creating canned reports and pre-formatted analysis for business users and data analysts in terms of trying to understand what happened and why did it happen. Obviously, the last sort of 5 to 10 years, a great growth in terms of sort of self-service visualization and a move towards being more user-driven. Especially for data analysts, but also for some business users as well. And alongside that, obviously, we've seen the emergence of sort of the data scientist as a role, and clearly, with statistical modeling and machine learning, there is definitely a shift there. Well, not a shift. Those are very much user-driven environments, user-driven tools, and increasingly automated as well in terms of generating data about not just what happened and why it happened, but what potentially will happen in the future. Why is it? What is happening? Right now, and also increasingly in today and into the future, developing applications that actually can influence what happens in the future through prescriptive analytics. And so here we see that actually the end users of these applications could be business users and data analysts. But the point here is that the through the application, the results of that analytics process is delivered not as in terms of data that needs to be analyzed and a decision to be made, but in terms of things like recommendations that the end user can simply act upon rather than having to reach their own conclusions about. Obviously, if we think about the way this is evolving and the emergence of artificial intelligence, or not the emergence, but the enterprise of adoption of artificial intelligence and machine learning, there's some different terminology that's used, and it's always good, I think, especially from our perspective, to just highlight what we mean by these different terms, because we do see them being used somewhat interchangeably. But if we think about sort of artificial intelligence at a high level as being sort of the quest to build software running on machines that can think and act like humans, then we see that machine learning is a subset of artificial intelligence focused specifically on using algorithms that learn and improve without being explicitly programmed to do so. And then within that, we see deep learning as being a branch of machine learning, based on a specific set of algorithms that attempt to mimic the human brain in the form of multi-layered neural networks. And obviously this illustration is again, sort of deliberately simplified and generalized. Obviously the deeper you go into this, the more complex it becomes. It becomes, a lot less simple. But, at a high level, I think these are the way in which we at least are using these terms within our research and ongoing within the presentation here. So if you think about, the key ingredients for machine learning, and I think, we see a lot of organizations trying to figure out, well, what do we need to have, what do we need to do in order to take advantage of machine learning? We would see there's, a combination of four things: so data, algorithms, compute resources, and skills. And starting, looking at algorithms, I think one thing that's interesting here is, whilst there is obviously ongoing evolution of the algorithms, actually a lot of the algorithms that the organizations are using are not new. They've been around for many, many years. A lot of them available as open source and freely available. So what's different here is it's not actually the algorithms themselves, but the ability of organizations to take advantage of them in an efficient manner. And, one of the ways they're doing that is because of this, back to what we were saying about, this increased volume of data that is available, but also, the more economic opportunities to take advantage of processing that data through freely available, or not freely, but widely available compute resources. And especially we see the cloud as having a significant role to play in terms of organizations being able to both store and process large volumes of data that is necessary often for machine learning at an economic point which is much more reasonable today than it would have been just 5 to 10 years ago. Obviously, the fourth part of the puzzle here is skills, and this is in some ways sort of the hardest part of all. Obviously, the skills to take advantage of these algorithms and compute resources and process this data are somewhat hard to come by and also expensive to hire. I think we do see some improvements there. Obviously, clearly this is an attractive area for a lot of people, so the number of people with skills in this area is growing all the time. Also, we see that the applications and tools and platforms that are available are increasingly making these capabilities available to let's say less technically skilled users all the time. And obviously there are limits to that to some extent, but it's increasingly available to more and more users to at least incorporate to some extent within their analytics processes. So beyond those key ingredients, when does machine learning potentially work? What are the key areas that we think organizations need to be thinking about to understand if machine learning is potentially applicable to them? There's a few of them, and I think one of the primary ones is really, and this is not to be overlooked. I think we have a tendency to think about this from a technical standpoint. Do we have the technical skills? But absolutely, clearly, what is fundamental here is to understand the business problem and the business rules thoroughly. Because unless you do that, you can't necessarily take advantage of a machine learning-based approach to automating and improving those rules in regards to delivering an improvement in terms of the business problem. So in terms of both that understanding, that domain knowledge is obviously important. We already talked about the volume of data that is required. Also the ability to, from a business standpoint, to identify good and bad outcomes. What are the potential advantages you want to achieve from putting machine learning into practice, and what are the things that you can identify that perhaps you're heading down the wrong route? And that's, again, it's really about the domain knowledge rather than any sort of technical expertise. And again, also as well, in terms of understanding the likely impact on the user experience. Again, it's sort of domain knowledge and understanding, the customer, understanding the end user and what impact it is going to have on them. And also, finally, in terms of the data, is the data applicable to being stored and processed in the cloud? As we said, cloud isn't a requirement necessarily for machine learning, but obviously it does give certain advantages. Either, is the data suitable to be stored or processed in the cloud, or, is the organization comfortable with storing and processing that data in the cloud? And then thinking about, some of the use cases. So we've outlined this in terms of what we call our sort of AI automation spectrum. So dividing up sort of use cases roughly into sort of three areas. So industrial automation, which includes intelligent systems, robotics, warehouse operations, smart factories, etc. What we call perception automation, which is much more in terms of sort of the replication of human perception. So things like speech recognition, natural language processing. And then what we call engagement automation, which is sort of the application of some of these capabilities specifically to drive more directly sort of some of the commercial initiatives through things like improved customer engagement and improved customer service, which is one of the key examples that we see. And so things like virtual assistants and chatbots and obviously some more traditional things like segmentation and recommendations. And so, we can apply sort of different technologies and different use cases across these three elements in the spectrum. But I think the important thing is, this is a spectrum, and what we do see is that there are combinations of capabilities from across the spectrum that will be combined to deliver, a specific use case. I mean, if you think about it in terms of, say, a retail example, and a customer being recommended with a potential purchase, obviously there may be some sort of image recognition or speech recognition involved in terms of identifying the user, virtual assistant or sort of chatbot technology in terms of engaging with them, some customer segmentation obviously behind the scenes and a recommendation engine. But also it's not just about, who is the customer and what are they interested in. It may also be about understanding what are the stock levels back in the warehouse in terms of both what has the company got a lot of that they want to sell, and also what can they deliver quickly, to that user based on their location and things like that. So it's a whole combination of capabilities that will come together in terms of any particular individual use case. I'll actually open up these. I think one of the key points here is that we think that machine learning and predictive analytics has applicability in every industry to some extent or another. Obviously, there are some key industries that are absolutely fundamental. So I've mentioned retail already. Manufacturing is also another one in terms of sort of predictive maintenance and monitoring and just-in-time production and demand forecasting. Healthcare, life sciences, also in terms of things like proactive health management and real-time alerts and diagnostics. Financial services, obviously a key sort of adopter of new analytics technologies, and definitely the same this time in terms of things like risk analytics, credit scoring, anti-fraud recommendation engines, targeted offers, but also some of the less sort of traditional sort of big purchases of data processing and analytics, but with some real definitely some real examples in terms of travel and hospitality, in terms of, again, it's about experience optimization, but also things like traffic management and scheduling, and dynamic pricing, and then in oil and gas, things like predictive maintenance monitoring again, and anomaly detection, but also seismic analysis and risk analysis analytics as well. And I think, whatever the various examples and opportunities are, we do think that they actually share some common characteristics, at least at this stage. So we'd say that the tasks that are performed are often actually somewhat repetitive and mundane, or in some sort of niche use case involve situations where the human wouldn't necessarily sort of place themselves due to danger. But we really see that they are performing tasks that are currently performed by humans, but not necessarily directly displacing them from their entire jobs. Obviously, this is a somewhat controversial area. It's something that we're definitely going to be continuing to focus on and analyze as we see deployments roll out at a greater scale. But at this point, at least, we see it's very much complementary. And thirdly, we see that the business value is in the data in terms of both the input and the output, rather than the algorithm or the model itself. But obviously, all three are requirements in terms of getting at the ideal end result. And the other thing I think is important, especially when we're thinking about AI and the potential of machine learning, it's easy to sort of jump ahead and think about some of the sort of potential long-term opportunities. But I think it's important if we think about the existing near-term opportunities. In many cases, we said they're fairly potentially sort of somewhat mundane. And we definitely see that initially organizations are using AI to sort of automate existing models, things like linear regression that rely on existing proven business processes, rather than trying to sort of, come up with something entirely new. Over the midterm, we see there are therefore opportunities to enhance those models using machine learning, to enhance both the models and the business processes. And in the longer term, the benefits will be more revolutionary in terms of, potentially, inventing new business opportunities, new business processes, with which, for example, to improve customer engagement. So, it is very much sort of a long-term trend towards the ultimate goal. Just one thing, just wanted to finish off here thinking about a specific example. I touched on sort of a retail example earlier. I was going to go into a little bit more detail on that. And, I think it's important if you think about how sort of retail engagement has changed over the years, from sort of in-store to online, from retail assistants and chatbots, personal shoppers recommendations, sort of broad loyalty rewards, moving towards more personalized offers. And the way in which we sort of see this sort of playing out in a retail environment, if you think about, how, traditionally you've gone into, literally into a physical store and engaged with, with someone within that store, it has been very much a person-to-person environment. It's a physical relationship of sort of help, advice, suggestions, etc., provided by that individual. And it's actually not until the transaction has been completed that is entered into the systems of record, and then obviously that data pulled across into the systems of analysis available for analytics. What we've seen, there's a number of changes in different areas over the years. So one is that those analytics capabilities increasingly being brought to the data within, either a data warehouse or obviously within a Hadoop environment, but also, as I said, more fundamentally, perhaps, within the retail environment itself, that shift moving towards online engagement rather than the person-to-person. So that role played by the employee in the bricks and mortar environment is shifting towards chatbots and digital assistants. And that obviously is true within a sort of an e-commerce environment, but even so, within actual, a bricks and mortar retail environment, and increasingly see the engagement with the customers is through a device, either their own device or one that's provided by the retail store. And so, things like recommendations and potential purchases and offers are being automated and delivered by those systems of engagement, rather than the employee. Now, in order for those systems of engagement, the actual, the applications to deliver those kind of recommendations and offers in real time, there needs to be some sort of systems of intelligence, as we're calling them, behind the scenes that are actually driving those decisions, driving those recommendations, and those need to be operating obviously in real time, often driven by the results of sort of machine learning models that have been created in the offline and the systems of analysis using historical data, but the systems of intelligence combining those models based on historical data with real-time data in order to deliver the offers through the applications that are the systems of engagement. So, we've rattled through there fairly quickly in terms of some of the key trends, and there's a lot to cover because there's a lot of other interesting things happening. But just to conclude at this point, I think, we've seen obviously that data growth is an ongoing challenge for lots of organizations, but, that decreasing cost of storing and processing data is alleviating that challenge to some extent. We've seen also that, on that basis, it's now more economically feasible to store and process data, that was previously ignored due to the sort of cost and functional limitations of traditional data management technologies. Based on that, we see a growing case for sort of AI and machine learning capabilities. It's important, I think, to think about the fact that the near-term use case for a lot of those capabilities is actually probably based on automating existing models and existing proven, business processes, and will later be applied to sort of enhance those as well as inventing new approaches. Those emergence of intelligence-driven applications that operationalize the information generated by data science and deliver it directly to business users, or even potentially directly to customers via those systems of engagement, is driving new approaches to data processing. Those systems of intelligence I spoke about on the previous slide, and it's while those systems of engagement are deliver the user experience, it's the back-end systems of intelligence that provide the automation of data-driven decisions delivered, as I said, through those operational applications at the speed of business. So with that, I'll thank you for your time, and obviously happy to take questions on that or any other aspects of what we're talking about here as we get to the Q&A session later on. But for now, I'll hand you over to Kevin and Brent, obviously, to talk about their experiences in this field.
Hello, everyone. My name is Kevin Lyons, and we're going to turn now to discuss a system which we've developed in-house for online learning. And just to sort of tie it back to what was being said by Matt earlier, we really are talking about, at the end of the day, a prescriptive machine learning system that brings together massive data sets, cutting-edge algorithm, incredible compute resources, very, very scarce data science, machine learning expertise, and perhaps most importantly, fully automated machine learning command and control structures and systems. All of this to better sell stuff through customer engagement automation. More specifically, we're talking about creating a fully automated, fully embedded process that automates marketing-oriented lookalike models. That automates marketing-oriented lookalike models, or more technically, supervised classification models, to build more profitable digital audiences at scale. So the overall use case, we use the system for a number of different reasons, but we'll just pick one use case here. So what we're doing here is we're basically trying to take a high-value seed and extend that out for marketing purposes. So perhaps the high-value seed is a group of people that go to a retailer's website, buy a flagship product of theirs, and spend a lot of money very profitably. And the retailer, but there's a good number of them, but the retailer wants to find more people that they can target and market to. So they find out what the characteristics, so we find out what the characteristics of these high-performing customers are, and then we go out and use massive amounts of data in order to create pools of tens of millions of devices and people and households that we make available to marketers for targeting. So someone goes to their website, buys a great product. We figure out what they look like. We create lookalike audiences to create tens or hundreds of millions of devices that are similar, and then we push that out to trading desks or DSPs or any number of marketing environments where these people can be found online for targeting purposes so that they can get more sales. Okay. Now, traditionally, the way this process works, it looks something like this. You gather data, you build a model, you validate the model, you deploy it, score the records, and monitor performance, and it's done usually by a human being. This is the old way of doing it. This is how I was doing it in the 80s. It works pretty well. People have been making lots and lots of money doing it this way. The only problem is it works really well when you're trying to create, say, 30 or 40 models, leveraging billions of events and create creating hundreds of scores, which we were doing here way back in 2012. But now we have over 80,000 models, leveraging trillions of events and creating trillions of model score events every day. So our data scientists were very happy in 2012, and we realized very early on that the time would come when they weren't going to be happy anymore. And we really did not want to scale out with data scientists. It's expensive and they're hard to find. So what we really needed was a system that automatically creates as many models as we want, when we want them, and that dynamically adapts in real time to changing conditions. Specifically, we want something that creates and validates and ships and monitors models, and that can do that at the scale of tens of thousands or hundreds of thousands of models. Specifically, we wanted something like this. We wanted the machine to do it. We wanted it to be fully automated with no human in the loop, completely automated.
So the idea with batch learning, with online learning is very different than batch learning because it updates with the immediate flow of events. And this is very important. And we saw this from the very beginning when we were doing some test cases. Back in 2005, when we were really just piloting this, Greece, you may remember that Greece got downgraded. And we were doing a pilot model for an investment company that we work with and still work with to this day. And they had some bond models in place that basically trying to find bond buyers. And the batch models we had in place for them just crashed. They stopped working. Performance was terrible. And these online learning models also crashed. Their performance was terrible. But with a batch model, you have to like start all over again and rebuild it. It could take a day or a week or something. The online learning models just basically within a couple hours understood the environment had changed and automatically, without any human intervention, completely changed the scoring algorithm by itself, and then you could see the performance coming back after a couple hours. So to compare like batch learning and offline, batch learning or offline learning a little bit more to online learning. So batch learning is like large-scale data schlepping, large-scale data storage, lots of painful data aggregation, lots of manual everything. Online learning, it's event level. It analyzes the actual real-time data stream. There's very limited data storage, and for this, you'll hear how we leverage Aerospike from Brent very soon. We have very light data aggregation, and it's lots of automated everything. So the whole idea is what we can do with literally with a click of 4 buttons, very easy. We can build a model, and within hours, if the data set's sufficient, it's live and scoring and making decisions and pushing audiences out to our business partners. Some technical mumbo jumbo, if you're interested. It's technically a stochastic gradient descent model with L1 regularization. We tried L2 and ElasticNet, and that didn't work any better. We actually are doing small micro batches, so we analyze maybe 100 events at a time, but that takes that's microseconds or milliseconds. We validate and monitor all the models in real time with something called DSBot, which is a homegrown command and control center. And DSBot also alerts all of our team members if ever anything stops working exactly the way we want it to.
Cool. Thanks, Kevin. So my name is Brent Keator. You heard earlier, I'm VP of Infrastructure here. So what I would like to do is, Kevin kind of explained a bit about, why we're moving in the direction from, offline, why we had from offline to more the kind of online learning approach with modeling. So I want to dive more into the how aspect. Dive into kind of, under the hood, technically what's there from an infrastructure perspective, but talk about, functionally what we did to adapt from what we have, from starting when Kevin mentioned 2012 and to now, as well as look at, how we're able to sustain long-term, as well as look at, scalability and the challenge that we faced on trying to increase on those volumes when we're talking about 30 to 40 to tens of hundreds of thousands of models. So from what we had from an offline layer, this is just kind of a light level look into our infrastructure, footprint from our serving layer of how we're handling the offline events and their modeling in the past. There's 3 major components. We have a serving cluster, which we call Espresso. We have a modeling cluster as well, which we have a name for as well, Extreme. And then we have a key value store for housing all of the kind of unique users and their kind of event history and segment history associated with them. So this is already in place. The serving infrastructure would handle all of the online events, so essentially pixel tag calls or fires from all partner sites, as well as offline files that are essentially transformed into messages and ingested from a pub sub style model through Kafka into our infrastructure into the serving front end as a centralized entry point. From here, the kind of configuration areas we've always gone with kind of a commodity style footprint for infrastructure. So it's basic, 40 core, 64 gig RAM, light on the SSDs because IOPS are less important. That we've moved to kind of streaming as opposed to log writing and shipping. Currently, we have a footprint in US, the EU, and this year we're building out in Asia Pac. So it's roughly about 5 data centers, 3 in the US, 2 in EU, and about 300 or so servers that we have for HA across these locations for supporting kind of the offline approach. The other component is the modeling cluster, and this is where we do all the kind of scoring and validation that for the events that are triggered in. This is about the same type of this is the same configuration when it comes to the server specs. It's about a third of the infrastructure. We're always performance tuning to get the most out of our resources when it comes to servers. And this basically we use Aerospike as the main key value store. We have an SLA for all these events for particularly online is about 250 milliseconds. So we have to have something that's super fast and handles reads and writes. We have probably 60-40, maybe 70-30. Basically, we do all of the user IDs or device IDs are stored within this database, and we do a lookup that exists and updates it or creates it if it doesn't exist. So this has been traditionally how we've handled it in the past. And so, looking at the kind of challenges and endeavor of online learning to figure out how we could handle something similar, we tried to leverage some of our experience in the past to build out infrastructure footprint that would make sense. We knew Aerospike's performance, and so just diving in more on that. You can see on the left side, spec-wise, it's if you're interested, it's essentially CPU is very minimal, but disks we use the Intel S series, and we have probably about 50 terabytes of unreplicated storage for all of our 2 different namespaces for all of our unique users stored there. But we do 94 to 99% when all of our read and write transactions in less than 1 millisecond. So we're able to cut down on the amount of time that's required in our full kind of transactional conversation to keep it within our SLA. So we knew performance-wise there, so we decided to use Aerospike because we need a place to, as we're building out our infrastructure for online learning, is a place to store all of the models, to keep it persistent, to have it readily available, so we can actually train and deploy these predictable models out to their different outlets like DSPs and whatnot, and then still maintain them on a regular basis. So we leveraged kind of the experience at Aerospike to deploy some similar. Spec-wise, very minimal. Models are roughly pretty small, so we could use small local disks. We're even currently evaluating storing it in memory. Nothing too grandioso when it comes to high performance hardware. It's just very minimal. Most of the work is done from a software side of it from Aerospike. The other component is do we build a new stack to handle it, or do we leverage exactly what we have? And essentially our just to top right here, Extreme, this is our modeling cluster. So this is the framework that we're currently doing for offline. And as Kevin mentioned, we would score it, but then you may not, build the model for, some time later. And so it becomes slightly somewhat out of date. And so we decided that we could leverage the same existing infrastructure because all of necessary data is already flowing through these veins of the stack. Processing wise, we're always tuning. We're very familiar with it. I mean, it's essentially, Java application, J clusters with, running J groups with different JVMs for handling offline and online. Performance scalability is something that we've built that we could easily scale out horizontally. Minimal hardware specs that are required, and plus the scoring was already built in. I mean, we already had that mechanism in place, and now we could essentially leverage the same veins. Instead of doing it for offline, we could look at it doing it for online as well. So we were able to essentially look at tying the key value store as a place to house the models and keep those updated, and then essentially, using the existing framework to help bring live the actual online learning into our environment. And this is just looking at it from a functional level, but just to recap, like Kevin talked about from, batch models is very slow. You're moving at your one-time validation, whereas online learning, you're doing more streaming, downsampling, you have to do data cleansing. You're keeping up at real time of what the changes are that are going on in the ecosystem or environments out there to make sure that your models are staying, current and, no longer have to do it for refresh. So it's definitely something that heavily interested, from our side. Essentially diving a bit more, just to kind of go high level into kind of the process flow of what we're looking at from our online learning, from a high level aspect of it. This is the look of it. So the first phase would be something like an event classification. So, kind of customer driven. You're essentially labeling, customers defined target audience. If you're looking for a retailer that's on, flagship products, and then, you can figure out who would be your quote unquote converted or non-converted users there, who you're looking for to build a lookalike against and be able to, essentially train against that set. So you're taking all the events that are already flowing through your systems, and then you have a labeling mechanism to it. And now you can easily customize what you're looking for against these pre-existing events. And it's real-time data is constantly flowing through the system. And so the next step would be data set preparation. And so this is kind of where you're handling, different anomalies that are out there, so you're not skewing the results. And so essentially you're handling the kind of burst tolerance and the duplicate entries. You have a lot of heavy, internet users that you don't want them to kind of skew because you're looking for a sample size and it's only that handful. You're not getting a full picture of all the users who are out there. So if you want to make sure that you're handling those to get kind of the reach across the audience or the data set that would benefit from a targeting or at least reach the most number of people. The feature selection is the next phase, and essentially you're looking for what features or aspects that you're interested in as you're training it. And a lot of this is essentially automatically tuning, as Kevin's mentioned in kind of the grease example. This stuff is tuning based on what you're ingesting into the system and actually customizing. But the blacklist and whitelist, the blacklist would be just as it sounds. You would limit exactly what it wouldn't take in, and you take in all the rest of the feature aspects, and then whitelist would be just what the aspects that you're interested in or the features you're interested in. So part of the process after preparation, you're doing some sort of feature selection around it, and then it comes the training part. So you're doing a model validation against this data set, data that's flowing through the system. You're basically taking we take a sliding window. We do about 60 to 40 non-converted to converted ratio. We take to double check, but a sliding window, I think we're taking about 10,000 events to kind of build this and train on a regular basis and refresh it and make sure that we're kind of staying within over time. You can do essentially you're setting different metrics around it or high waters around like lift, precision, recall to make sure that whenever your model's ready to be deployed to production from there. And then once you're ready, you can essentially, you don't use the same training set. Now you're looking for new users. You've created a model that you can push out there to do predictive analysis, and you can break it down and essentially score these events that are coming in. And if they match and become converted, then they get shipped off to the different, trading desk platforms to be render additional revenue for those owners of the data or the targeters for it. The scale, accuracy, trade-off. Obviously, the more people you want to reach, you're gonna take a hit on some of the accuracy, and vice versa. So you have to kind of, there's some tuning you can decide on whenever you're looking to kind of, build your models or target reach for your target audience. So high level, that's where we are. So we talked about a little bit of functional. We talked about a little into the kind of level look into the process, but also we want to make sure we're building something that could scale into the tens of hundreds of thousands. If we're talking 30 to 40 models from offline into, online world where we're talking, that magnitude of difference, we wanted to make sure that we had an infrastructure solution that could handle it. Functionally, using the existing infrastructure and Aerospike helped. For the throughput, it's important that we weren't just focused on a single data center, and that we were looking at things that we could benefit from like Aerospike from XDR, and that's XDR gives us the cross data center replication that allows us to have the existing model for, available in all the other data centers within that region at the same time. So you could score, and you can bring up the number of events you're triggering against that particular model. So you're able to kind of scale it out as needed. You get persistency across all of the clusters that you have that carries that same namespace, and the replication feature is already built in, so it makes it a lot easier in the enterprise stuff. But so for the ring for replication, is kind of just taking a look at US, and as I mentioned, we have a similar one for EU, and in APAC we're building out now the different serving provider. But for US, essentially we use bare metal cloud, which is from a hosting provider. I guess in this case it's Internap. It allows us to kind of stay ahead and current with specs. We like to take advantage. Aerospike it takes advantage of additional IOPS when you're talking about new disks that are coming out. Like right now, we're actually doing some tests with the new Microns, the 9200s. We're seeing roughly 10x performance we receive from our Intel S-series SSDs. So we're constantly on a 12-month basis refreshing hardware to reduce our footprint for overhead management, as well as increase performance to stay with the actual trends, instead of investing in kind of a cap cost for that particular infrastructure to handle the workload. We do kind of a private connect between our sites. We leverage a backbone platform connect there. I think roughly we are around I think we are at 30 gig asymmetrical between these sites now. But we're staying current within a minute or less than a minute on any of these types of models being available, sub-seconds in most cases. Especially with the online learning, since it's a different flow in a separate cluster, it's essentially readily available in each one of the locations. We use for LVS and kind of a traffic management, GSLB, and then the XDR to give us that HA as well. If we lose a site, then we can handle it elsewhere, but the cluster is pretty resilient. And just to touch a little bit on sustainability, obviously we can build something that works, we can build something to scale, but we need to make sure that we're keeping an eye on it. With the offline stuff, you need extra set of eyes to kind of refresh on a regular basis. With online, you're talking a much higher scale. So building in additional monitors to handle the thousands of models, essentially you're giving the power to users to create. So you need to make sure that you're watching over those to make sure that they're working more or less. And so we have separate monitors that we've used. One is on the Extreme Lab framework on the actual modeling cluster, where we use some JMX-based monitoring with integrations for alerts to address things that are driving errors or not reaching the thresholds that we're looking for. We do log aggregation to be able to see from a higher level on how we're handling from an online learning perspective, how these models are performing. And then, as Kevin mentioned, DSPOT, which is pretty neat, that we built in-house, and essentially it's a place where you can actually watch the models and manage them in real time and make adjustments if any manual intervention is required. This, in the sake of time, this is kind of just to recap from our perspective, the kind of evolution from the offline to online, and we're continuing to develop in that front and automate more and more. But this is a look from a technical perspective in how we were able to accomplish it, and we're continuing to grow it.
Fantastic. Well, thanks, Brent. So now we'll take some questions from the audience. So there's still some time if folks want to enter any questions they have for Brent, Kevin, or Matt. So with that, I'll get right to it. One of the first questions is, Brent, you had mentioned that you are working with Internap and working on even like updating your hardware. It seems like on the order of almost every year, if that's right. Otherwise, how are you managing your data growth? You mentioned that there was 50 terabytes of data, but is that growing? If so, how much, how readily, and how are you managing that? Brent, you still there? Okay, let me shift gears. Maybe Brent's audio is on mute. So the flip side of the question is for Matt. Matt, what types of growth in AI ML have you seen in terms of data sets, and how are people managing that? It's kind of a concern from the audience.
Yeah, I mean, I think obviously it is something that is potentially concerning. Obviously, one of the key points that Kevin and Brent made there, but in terms of sort of when you've got a small number of models, and obviously perhaps it could still be a large amount of data, but perhaps a focused data sets, then it's obviously easier to manage that. And I do think we've seen some companies that have been challenged with that in terms of enabling that growth that they want to achieve. Obviously, if they're initially successful, I think this is one of these areas definitely where one successful project potentially leads to many more. But obviously, the challenges of managing that level of data and obviously the operationalizing those models also increases as well. So it's definitely a key concern.
Yeah. Brent, Kevin, just let me know if you're back online.
Yeah, we're back. We had to dial in a different way.
Fun. So kind of the question is, what kind of data growth are you guys seeing? The audience is a little concerned, like, hey, I've got models running. What kind of data growth are you guys seeing?
I think in general, from an infrastructure standpoint, you kind of plan for these orders of magnitude of additional growth, and you kind of have to. I think Matt touched on it. You're seeing more and more growth almost exponentially into the system, and you want to be able to use that to help model and see more of the audience. But from an infrastructure standpoint, you can take advantage of when you do something like an internet app or bare metal provider where you can actually do leasing for periods of time. You can take advantage of the cost efficiencies associated with newer chipsets throughout, the performance gains there, as well as the density of disks and performance of the hardware as the kind of growing hardware sector is planning for the same type of data growth, so costs are driven down from that side of it. Planning-wise, I think we've grown from a year ago we were about 35, 40 terabytes up to 50 terabytes now. It's good. I mean, as we're planning and we are growing our clusters accordingly and manage them from the data growth on a high water mark, and we set all the thresholds in place to be able to either grow it or scale it out horizontally by additional drives, additional IOPS if needed, additional memory. A lot of this stuff is pretty flexible when it comes to the infrastructure side. And then we look at regional. We set up different namespaces with regions there. I don't know, from a modeling standpoint, it's important. The more data that we have, the more we can make use of.
Yeah. So one of the reasons, Kevin, one of the reasons we implemented this system is that our data can change rather rapidly with additions and subtractions of key variables. And when you have a more traditional batch method, the batch method offline, it has let's say it has 1,000 variables. Those are the 1,000 variables that you're allowed to use within the system for scoring. And if you lose some, you can lose some scalar accuracy. And if you gain some, you won't take advantage of them until you rebuild the batch model. Online learning doesn't need that. It just consumes, if a data variable disappears, it'll just start learning without that and adjust to it automatically. If a new data variable appears, it'll just consume it and start using it and learning from it.
Yeah, and so the next question has to do with, is that at the single model level? You indicated you had 80,000 models. What would an individual model in Nielsen's case be?
What would it be?
Exactly.
I guess the way we would define that is 80,000 self-learning scoring algorithms, separate scoring algorithms that are independently scoring against the stream of data we're seeing. each one creating hundreds of millions, billions potentially, of different scores for different purposes. So essentially, each one represents a different, if you will, audience or decision being made.
Scenario, okay. And so back to Matt, is that typical, how does, I might suppose, is that on the high end across different industries? How many different models do you tend to see across the industries that you've encountered?
Yeah, I mean, I think it obviously, as your question suggests, it varies from industry to industry, and also the extent to which organisations are already deeply engaged. I think at this point, we would see sort of in sort of marketing and customer engagement at the perhaps more advanced and at the higher end, and obviously a lot of other industries. We talked about that spectrum when we see some of the use cases that perhaps on the on the industrial automation side. There may be a lot of data points, but in terms of the extent to which organisations are taking advantage of those, it's still early stages. So yeah, I'd say it's probably at the higher end, but just the nature of sort of the level of adoption in other areas today.
Okay. Yeah, so believe it or not, we're up against the hour right now, so I'm going to cap our questions. We'll get back to individuals with questions that we did not get to. I want to thank folks for attending the webcast. Also, obviously, want to thank our presenters, Matt, Kevin, and Brent. As a reminder, this will be on demand. It will be available on Bright Talk shortly. And on behalf of Aerospike and 451 Research, thank you, everyone, for attending. Have a great day. Thanks again.
Bye-bye.